be discussing about rule based expert system, and we will also mention some things about certainty factors. Although we will have separate lectures on certainty factors that demands a little more discussion. Now, briefly, while discussing about rule based systems, we had talked about expert systems, and if we quickly recapitulate what we had learned about rule based systems, then there are some salient points that we should remember. First, let us quickly have a look at what are the things that we need to discuss about expert systems, rule based systems. First, the execution cycle. This is just for your recapitulation. This means that there are three phases. One is match, one is select, and the other one is execute, and after that we come back to the match phase only. And the architecture of a rule based system consists of a knowledge base, which we can write for short as KB. There is an inference mechanism, which we are writing IM, inference mechanism or control structure, and there is a working memory. In this working memory, all the current facts are being stored, and the user, there is another user interface, as it should be for any system, and the user interactions are through this user interface, and that is communicating through the inference mechanism, and the inference machine reads and writes in the working memory, reads from and writes to the working memory, and the knowledge base consists of rules in case of rule based system. All right, rules. And it is needless to say at this point that rules are of the structure if antecedent then consequent. Now, if we look at this cycle, then let us again see what does the match phase, what is done in the match phase. The inference mechanism looks at the data for the current problem from the working memory and tries to match them with the contents of the knowledge base to see which rules are enabled to be fired. Okay. Now, there may be more than one rule which are enabled to be fired. When is a rule enabled to be fired? A rule is said to be enabled to be fired when all the antecedents match or the consequents match, okay, depending on whether we are going to do forward chaining or backward chaining. If more than one rules match are applicable at a particular cycle, then the select phase, which is also known as the conflict resolution phase, in this a subset of the rules are selected, maybe one or maybe two, and those rules which are selected are only fired, and as these rules are fired by the inference machine, new facts are generated which go to the working memory, all right, which come to the working memory here. Now, that will enable other rules to be fired, that will enable other rules to match, and this cycle will go on until no further rule matches or the goal that with which we started the system is met. So, these were 2 points, but besides this, there are a couple of other points which we need to recapitulate. That is about the inference mechanism. There are two types of reasoning that we had talked about. One is forward chaining and the other is backward chaining. All right. In forward chaining, which is also known as data driven search, we start, say we have got a rule like this: if A and B and C, then P. Now, given a rule like this, in the forward chaining we try to, here is the whatever is there in the working memory, say A, B, C, we start matching the contents of the antecedents, and if all of them match, then we say that this rule is enabled, and if this rule is fired, then the firing will produce this P as a new fact in the working memory, and this can enable further search. On the other hand, in the case of backward chaining, we start with the data, we start with the goal, not the data. Unlike the forward chaining, in the backward chaining case, we start with, say we have got a rule like, say backward chaining, if we have got a rule like if A and B and C, then P, and there are other rules also, and we find that I have to prove P. So, I then try to see, I start with P, and that tells me that I have to prove A, B, C, and maybe in the working memory A and B are true. So, these are solved, but I have to find a rule which has got C in its consequent. Suppose X is also there, then C. Then after this, since C is my goal, then I start with C and see whether this is proved or not. For that I have to fire this rule, C is true if X is true, and so in order to prove C I have to prove X, but X is already proved. So, therefore, C is proved, therefore, P is proved. That is backward chaining. Now, all these things we had discussed in our discussion about rule based system. Now, rule based systems have found a very important application in the case of rule based systems have been applied in expert systems. And what are expert systems? Expert systems are said to be AI's greatest commercial success, and an expert system uses knowledge specific to a problem domain. This is a very important point that we should try to understand, that it uses knowledge that is very narrow, specific to a particular problem, maybe fault diagnosis of a two-wheeler, or maybe fault diagnosis of a particular type of car. All right. So, the narrower you make the domain, the possibility of success of an expert system is more, because what we try to do in an expert system is to capture the human expert's knowledge in the form of rules. Now, human expert knowledge is a little complicated than can be really captured in the form of rules. So, if we can restrict our domain, then probably we can acquire the proper knowledge and encode it in the form of rules, and then also we will find that for that small domain, in order to capture all possible cases, we can have a huge number of rules. But so we are not really trying to match the human expertise or the human capability in any way in expert systems. But then the question can be asked, then why at all we go for an expert system? The reason is human expertise is scarce, it is costly. For all the aspects of problems, you will not find enough number of experts who can cater to all the possible large number of queries that come up. Think of specialist doctors. Now, specialist doctors are really scarce in number when compared to the demand that we have from a large number of patients. For example, real good expert cardiologists. Now, all the patients really do not need that level of expert advice all the time. There are some cases, many cases, which can be treated by less than an expert, I mean human expert. So, if it be possible to capture the expert's knowledge to some extent in such systems, then obviously we can provide better service to the patients. Everybody need not line up in front of the doctor's chamber, need not just wait for weeks and months to get an appointment. Maybe through some computer system, they can be given routine advices wherever that is good. So, although expert systems aim or attempt to capture human expertise, the gap will always be there. Nevertheless, for many applications, as we will see in many cases, where say for example, diagnosing the situation under a mine, when we have put in some sensors and we really want to interpret the data, either I take out the data above, I mean at an upper level and try to look at it, but proper interpretation of data at runtime may not be feasible for an expert to do. An expert system can do that job quite well, provided we keep the domain narrow. So, once again, so what is an expert system? Expert system uses, it is a system that uses knowledge specific to a problem domain to provide expert quality performance in that specific application area. Now, there have been a number of successful expert systems. Here we can see some of the names you can note down. Dendral, which was developed in 1967, is an expert system that determines molecular structure based on mass spectrograms. There is a typing mistake here. MySin, which was a very popular expert system developed at Stanford University by Dr. E. H. Shortleff in 1976 as part of his PhD dissertation. MySin works for the area diagnosis and therapy recommendation for blood diseases. It helps to diagnose different sort of, not only that, later on MySin was done for different infectious diseases as well, bacterial infections. Prospector, we will look at MySin in a little more detail in today's lecture. Prospector, which came very close to MySin in 1978, is an expert system that was used for mineral exploration. That means, it tried to estimate where a particular mineral is likely to be there, and it found about $100 million ore deposit successful, right. successfully. XCon is an expert system that was developed in 1984, but the predecessor of XCon is known as R1, and that expert system was again developed at an university, and later on it was taken up by the Digital Equipment Corporation to configure large VAX and PDP-11 series computer systems, how to install them. Such large systems, installation of those require a lot of expertise about the layout, the cabling and other conditions, but that can be done judiciously by XCon. And this saved Digital Equipment Corporation, DEC, $70 million per year. Okay, so that shows the commercial success. Now, let us look at the common characteristics of expert systems. What are the common characteristics? Well, let us look at the first point. System performs at a level that is generally recognized as equivalent to a human expert in the field. Okay. It is better that you keep the domain narrow, keep the set of problems that the expert system can address limited rather than be too ambitious, but the success of an expert system would be measured by if I had employed a skilled person, an expert over there, paying him huge salary, he would have done the particular work, and for that work, if the expert system can do and show a performance that is close to this, then the expert system is okay for that domain. The reasons, as I said, human expertise is rare or expensive, and the demand for a solution, there has to be a demand for that solution that justifies the cost and effort of building the expert system. Expert system building, although we know the technology now, say rule based system is one, which we will be showing here, but it takes a lot of effort, time, manpower, programming time, testing time in order to make a real successful expert system. And so there has to be a demand for it. The system is highly domain specific, because even in a narrow field, lots of knowledge is there and we have to capture that. And it should be narrow enough so that it does not depend so much on common sense. Okay. Now, we have to run it using a machine. So, it has to be amenable to symbolic reasoning. We should be able to reason using symbolic methods like predicate calculus, propositional calculus, where we can represent the facts and rules in the form of symbols, as we have seen earlier. But it should also have a challenge that the solution is not straightforward. You cannot employ an expert system to sort a file or sort an array, or even do some pure image processing activities for which there are very good algorithms available. The methodology is absolutely known. You really do not need much of decision making expertise. The rules in a rule based system, rule based expert system will, in their if the situation is this, then do this, will provide those critical judgment in an expert system. If those critical judgments were not there, in that case expert system is not required. Again, if you recollect that match, select, execute cycle of a rule based system, in the select phase we are doing conflict resolution. That means we are selecting a subset of rules by some judgment, by some heuristics. We may assume that okay, that if we select this rule, that is bringing me closer to the goal. So, let me select this. So, it is not a straightforward algorithmic decision, and so for all those cases expert systems or expert system approach can be used. Presently, there are systems which are a little hybrid in nature, in the sense that they use some part of rule based expert system and some parts are solved algorithmically, and these two together provide a very good result. System can explain its reasoning. Think of the scenario that you have gone to an expert and the expert has told you that you have to undergo a surgery or you have to undergo a set of blood tests. You can ask the expert that why did you ask me, why do you want that I undergo this blood test? The expert will be able to explain to you why or what is the reasoning that went behind him. Maybe that he is suspecting certain certain results, there are some possibilities that that are there in his mind, and he wants to verify that or eliminate some of the possibilities. He will be able to explain that to you. Just as a human expert will be able to do that, similarly it is expected that an expert system will also provide that sort of explanation, at least close to that sort of explanation. It should at least try, we should attempt that it should give similar explanations. So, in order to be useful, it must be able to justify its advice or conclusions. Now, the basic architecture that we had said about rule based system remains unaltered here. Usually expert systems are rule based, although there are expert systems which have been built on frames, semantic nets and other technologies, but mostly rule based systems have found its popularity. Now, what are these rules for? The rules are to extract the expert knowledge in the form of facts and rules, and that is a real task. We will talk about this a little bit. Getting the knowledge from extracting the knowledge from the experts is really important and critical, and this process is known as knowledge acquisition. In order that an expert system becomes successful, the knowledge has to be acquired properly, and it is not a very straightforward case, because the human thinking model is no one is sure whether it is rule based or what sort of data structures it maintains. So, there is a lot of debate about it. So, often the experts talk from a level which may be intuition or which may be very deeply embedded in their knowledge, and they are so habituated they can click upon the a particular suggestion and they say that. But what is the reasoning process that went through to lead to this inference is often not very clear to the experts also. Therefore, it is necessary that a knowledge engineer, as we call it, must talk to the experts, understand the domain, and should be able to extract that knowledge and represent that knowledge in the form of rules, so that that can be embedded in an expert system. Now, so let us quickly look at the blocks. One is the user interface, one is the inference engine, there is a general knowledge base, and there is case specific data. Now, you can think of that, well, where is the working memory? The working memory is this for the time being. This is the rule interpreter, inference engine, inference machine, control engine, whatever you call, that is the part, and this is the knowledge base. and we have not deviated from the earlier architectures that we had shown, except for this might be that the case specific data can be directly fed here, but the interactions are the same, that the inference machine will read the data, try to apply, find out which rules are enabled, apply them, and on application new data will be generated over here. So, that will come. So, user interface acquires information and displays result. Inference engine performs deductions on the known facts and rules, that applies the knowledge base, and knowledge base stores the domain specific facts and rules for domains for solving the problems in the domain, and case specific data working memory stores information about the current deduction. So, these are the 4 blocks. Now, as we know, rule based expert systems have many options when applying rules. At the beginning of this lecture, I was mentioning about forward chaining and backward chaining, which is also known as forward reasoning and backward reasoning. And in forward reasoning, we start from the available facts and try to arrive at the goal. On the other hand, in case of backward reasoning, we start from the goal and try to prove the goal, that is, we start with the conclusion and try to prove the conclusion by finding the sub goals. A rule, if x and y and z, then p, means that in order to prove p, I have to prove x, I have to prove y, and I have to prove z. Now, so p is true if x is true, y is true, and z is true, but might be x is known or known already to be true, but for y and z I have to test them. So, again I will have to find a rule whose consequent has got y, as I was explaining at the beginning of the lecture. Similarly, depth first, breadth first, etc. are again 2 different ways in which this thing can be done. I hope you will recall what is a search space. Let me for a second recapitulate on that. I have got I am in a particular state, say S0. How is that state defined? That state is defined by the state of the working memory, some of the facts that I know of A, B, C, etc. Okay. Now, given this state S0 where A, B and C are known, I may have a possibility of different rules to be fired, R1, R2, R3, and firing each of these rules will lead me to different states S1, S2, S3, because each of these rules will derive new inferences. Might be P will be known to be true if I fired this. Now, on this new state I will again have different other rules to fire. If I had selected this rule, then probably I would have had some other different rules to fire, which I have not traversed as yet. All right. So, if I after this I have got these 3 rules to fire, I fired this rule and I come to this state, and that had 3 different paths, and I select this state and come to another state, etc. And while at every level I have left some paths unexplored. So, this entire space is the possible search space in which the path towards the solution lies, and my job is to find that out. And in order to search that particular path, we may have we may like to do depth first, like say out of these 3 rules I first take this, then I take, all right, say this. In this way I go on, and when I come to a dead end, I have not found the solution, I backtrack and follow the other unexplored paths. That is the depth first. In the case of breadth first, what would be the case? At this level, I will fire all these rules and come to this state. Again at this level, I will fire all the possibilities and come to this state, and I will try to explore the space in a breadth wise manner. Obviously, you know the difficulties of breadth first, that it will need a lot of nodes, lot of new children will be generated. Another option is heuristic search, which have been discussed in this course. Now, heuristics means with some partial information and knowledge, I would like to find a better way, possibly intelligent way to explore the path. Now, in that case, what do we do? In that case, probably at this level, I try to evaluate a heuristic function. Now, what that heuristic function will be is very much dependent on my application, and based on the heuristic function, I can select a particular path. All right. So, say let me erase this. Say I have, say, A, B, A on B and C is here, and from here I and D is here. This is my initial, that is some particular state, say S j. This is the state of this, and I want to come to another state, that is my desired state, that which should be A, on that there should be B, and so, and maybe here I would like to have say, sorry, I will change this. Say I want to have C to be placed here and D to go below B. All right. Now, that is my objective. Now, I have got different options to do that. Suppose, so I want to come to this goal state S g. Now, I have got one way that I can do is, I cannot really take C over here, C on top of B. So, I can have either, one rule can be that you come to a state where A is here, B is here, C is here, D is here. That is one possibility. And from there you take C above this and take B above this. Suppose it's all, suppose this is also allowed that if that be the, this be the case, then I can straightway come to this, that A will be here, C is here, and I directly take B on D. I take sorry, this is B and this is D. Let me make it cleaner. Say I put D on B. Now, suppose my rules allow me that I can directly come over here. Now, which one should I? So, this is another state, say S m, and this is S m, sorry, this is S n. Now, which rule I should fire? One thing that I can always see, that this one, if I have got a distance function, then this S n is closer to this, because this part of the problem is already solved in one move. all right, and this will require more number of moves. So, if that be my heuristic function, I can straightway come to the, I will apply this rule instead of this, because that will reduce my distance to the goal. Now, these sort of judgments are known as, are used in order to have best first search. So, apply the best rule, that is one approach. Another approach is you can apply all applicable rules. So, here is an inference example. Let us look at this. Consider the following rules about diagnosis of an auto car problem. Say R1, the rule R1 says, if there is gas in engine and it turns over, that means when you put it in, it is making that sound, but it is not starting, all right, then the problem is with spark plugs. If as you turn the key, it is not turning over, so that initial sound is not coming and the lights are also not on, then the problem is with battery. If it does not turn over and the lights are on, then the problem is with the starter. The fourth rule says, if there is gas in tank and there is gas, means petrol, in tank and gas in carburetor, then there is gas in engine. Now, suppose these four rules are known to us. So, this is the status of our database. We know, say, that there is gas in tank and there is gas in carburetor, and it is known that it is turning over. So, that sort of sound is being made, and our goal is to find what is the problem, and we have got all these four rules in our knowledge base. So, then our problem is, we have to find out what is the problem. Problem spark plugs, problem battery, problem starter, or what is it? Now, out of these, here we can see, out of these rules we can always find out which rule will be enabled. Now, we can see that rule R1 is enabled given this gas in tank, gas in carburetor and turning over scenario. Rule 1 is gas in engine, because rule 4 says that gas in tank and gas in carburetor, then gas in engine. Therefore, then we fire rule R1, first R4, then R1, then we know that gas in engine and turns over. Then we can find that using rule R1 here, that the problem is with spark plugs, right. So, then we come up with the solution that X is spark plugs by R1. Okay. So, we fire two rules. So, that is a typical, a very simplistic case of an expert system. Now, although this problem that we have just now solved has been solved with forward chaining, as you have realized that we started finding the rule that was matching with this gas in tank, gas in carburetor. So, R4 was enabled, and then in the next cycle, in that cycle we came to know the gas in engine. In the second cycle, this R1 was gas in engine and turns over matched, so R1 fired. But if we had done with backward chaining, how would you have done it? Just try it yourself. To make it more specific, suppose our goal is to prove that the problem is with battery with the same set of initial facts that we have given. These initial facts you note down. These are the initial facts. All right. Given this and the rules, given these rules, now you can try to solve it in backwards chaining, and let us see, you will see how it works. And what I want is that you will have to draw the search space based on the rules fired, not the entire search space, but the path that is traversed. How did the problem get solved? That tree structure you have to draw. Okay. Now, as I said, a very core part of developing any expert system is acquiring the knowledge from the experts, and that process is known as knowledge engineering. Knowledge acquisition is the bottleneck in developing expert systems. I was just mentioning that. For different reasons, often difficult, it is difficult to codify knowledge as facts and rules, that is, to convert them, first of all, to extract them. Extracting and formalizing or refining knowledge, this is a long, difficult and laborious process, and this process is known as knowledge engineering. Okay. The other thing that I was talking about is explanation facilities. These are imperative for acceptance of an expert system. Now, the MySin expert system had a nice front end developed, that is known as Tiresias, that supported knowledge acquisition and explanation, and it could answer questions like, why is that knowledge relevant? How did it come to that? How did the system come to that conclusion? What is it currently trying to show? And this interface also allows, because when you start developing an expert system, it will be too much to expect that at the very initial phase, your knowledge base will be so complete that you will be able to, it will not require any change, or you would not need any knowledge to be put in. We always learn, so an expert system should learn also accordingly. So, there should always be a facility by which you can add knowledge to an expert system, and that addition can be done by Tiresias in case of MySin. What is an expert system shell? Now, that is also another very important criteria. Now, as you can think of that, an expert system consists of the knowledge base, the inference mechanism, the working memory, user interface, etc. Now, as we change the domain of application, the first thing that will change for sure, is the knowledge base. But maybe that when I have taken so much trouble in developing one expert system and developed its inference mechanism, its conflict resolution strategy, its working memory structure and everything, then why I would not like to throw out everything. Instead, I would rather like to change the knowledge base and apply it in another application area if possible. That will reduce the development life cycle of an expert system. In order to meet this end, expert system shells have been proposed, and expert system shells are expert systems where the knowledge base part is empty. All right. So, out of that you just take out the knowledge base part, make it empty and allow somebody else to put in some other knowledge base on that. That is expert system shell, and such expert system shells have got the flexibility of giving you different conflict resolution strategies from which you can select depending on the domain, different sorts of inferencing, forward and backward reasoning, etc. And another thing that we have not yet mentioned at all is representation of uncertainties. The rules that we use in an expert system are often very uncertain. Okay. It is not always the logic is not as simple as 2 plus 2 4. For example, given a particular soil quality, a particular vegetable that will grow over there, experts can say that this relationship of a particular soil quality, a particular monsoon prediction will yield that approximately this amount of vegetable, of a particular crop. But all these are not absolutely certain, and there are some uncertainties always involved. The uncertainties come from different sources. The uncertainties in data, the uncertainties in our expertise also. For example, when a patient comes to a doctor prescribes a medicine. He has got an estimation from his expertise that this medicine will reduce the symptom within say 7 days to a particular level. But he cannot always be certain that within this 7 days this will reduce, that is one uncertainty. And the second thing is to how much it will reduce, it is not always possible to quantify, is not it? The fever, the frequency of fever, the headache will come down, how much? So, there are uncertainties in different levels, and we will discuss that separately. But in order to be successful, an expert system shell must provide some means of representing uncertainty. Typical expert system shells are, which are free here, any one of you can download it and try playing with it. Expertise to go. It is a free expert system shell where the shell provides the inference engine, knowledge acquisition and explanation interface. The user must insert the relevant knowledge base. Expertise to go light version is a Java applet where a very nice GUI interface is there, and there are features for knowledge acquisition, explanation, justification, etc. Now, here is a typical GUI where the expert system shell has been used to develop an automobile diagnostic system, and this is a GUI which is being shown to the user, so that the user can select the result of switching on the headlight is, we had just shown the example, they light up, nothing happens, I do not know. Now, see this sort of facility is also being given. So, your rule base must be able to capture those also, and if you are certain, either you are very certain or very uncertain, you can submit your response. You can also ask that why are you asking me this, and the system should be able to explain that. Okay. So, these are typical GUI. Now, in this say expertise to go, let us see typical rules that are there. This rem is a remark. We are showing a sample knowledge base here. Rem specifies a comment. The rule, we also put in a comment. Why is the rule? The rule is going to check, is the battery dead? If, look at these brackets which are the antecedents, if the result of switching on the headlights equal to nothing happens, or now this is a peculiar case where we are allowing disjunctions also, the result of trying the starter equals nothing happens, then the recommendation action is recharge or replace the battery. Now, depending on the shell that you are using, the syntax of the rule will change. So, there is one particular syntax, we will see a couple of other syntaxes also. So, in this particular case, say the shell is providing me with some operators like equals, not equals, equals one of, or comparisons. Say look at the rule, is the car out of gas? That is what I want to test. If the gas tank equals empty, then the recommended action is refuel the car. In that way we can write, there are rules, and the system also prompts, as it fires the rules, it also prompts for acquiring information. What sort of prompt? The result of trying the starter. What happens when you turn the key to try to start the car? The car cranks normally, the car cranks slowly, nothing happens. This is being shown to the user, and the user selects one, as we have shown through the GUI. Say for example, it is prompting a multiple choice, like the smell of the gasoline is present when trying the starter, not present when trying the starter. The user is asked to select, all right. And these sort of prompt actions are really activating this sort of GUI, that is being shown to you. The inference engine in this E to G light, Expart is to go light, that shell is the inference engine works backwards from a goal, it is backward chaining, obviously stops as soon as it finds a rule that concludes the goal with desired certainty. It handles uncertainties via certainty factors. Now, these certainty factors are really important. This is a very important method, but before that let me state that there are different ways of handling uncertainty. In the following couple of lectures we will be dealing with uncertainty management, different techniques of uncertainty management. The different ways of handling uncertainty, one can be probabilities, where we specify likelihood of a conclusion that or apply Bayesian reasoning, this part we will discuss a little later, and certainty factors, where certainty factor is an estimate of confidence in conclusions. It is an estimate of, it is an estimate which is provided by the experts. It is not as mathematically precise as is the case of probabilities, but it is also very effective. And MySin we must discuss for the next 5 minutes or 3 or 4 minutes about MySin. MySin is a medical expert system for analysis of meningitis infections. MySin uses backward chaining rule based expert system. It produces focused questions. It also produces a natural language like interface for communication with the users. Some typical rules here, quickly let us see. You will see that the syntax has now changed compared to the earlier one that we had shown. If the stain of organism is gram positive and there is no disjunction allowed here, the morphology of the organism is coccus and the growth conformation of the organism is clumps, if these three are true, then it's, remember, it's a medical case. We cannot say really with certainty. So what we will say is there is suggestive evidence of 0.7 some value that the identity of the organism is Staphylococcus. That is a particular organism. Now, this rule in MySin can be translated in a Lisp syntax like structure, where the premise of the rule is and there is a conjunction of, in the same context, that is the organism, stain of the organism is gram positive, morphology is coccus and conformation is clumps, then action is conclude context that conclude, that is Staphylococcus with a tally 0.7. Now, what is this 0.7 that we will discuss in the next lecture? But just to wrap up, that is a very key factor of MySin, that is a certainty factor. But the beauty of MySin is, look at, just let us have a look at the way it converses with the user. What is the patient's name? The doctor types in John Doe, male or female. This italicized parts, the system is saying. The doctor says male. What is the age? He is 55. Have you obtained? So, the system is also understanding this. The doctor cannot write that to my mind he is approximately 55, not that sort of, not a free flowing English, but he can, there is some restriction, but he can type in he is 55. Have you obtained positive cultures indicating general type? See how naturally it is speaking. Yes. What type of infection is it? Primary bacteremia. When did the symptoms first appear? May 5, 1985. Now, it goes on. Do you know the identity of the organism 1? No. Is organism 1 a rod or a coccus or something else? The doctor says rod. In this way, a very naturally flowing discussion goes on, and ultimately MySin comes up with a recommendation. my recommendation will be based on the opinion that the identity of organism may be, note this, may be Pseudomonas aeruginosa and other such E. coli and other such possibilities. On a scale, then it further, so this is my provisional diagnosis. On a scale of 0 to 4, it is asking the doctor where higher numbers indicate greater severity. How do you rate the patient's degree of sickness? The doctor says 3. And the MySin further goes on asking more questions and then comes up with a recommendation that there were so many possibilities, and just as an expert doctor, it says in order to cover for items 1, 2, 3, 5 and 6, give gentamicin using a dose of 119 milligram, 1.7 milligram per kg for 10 days, modify dose in the case of renal failure, and in order to cover for item 4, give clindamycin using a dose of so and so for 14 days. Just see how naturally a system can communicate, and that is what an expert system can do in order to come to a reasonable, once it is nicely built and it is restricted in a proper domain. So, to conclude, before conclusion, let us show a particular, let me give you a small quiz to deal with. These are, you have to answer this, say what is, try to answer which we have already discussed, what is an expert system shell. And the second problem I am just leaving to you, it is really challenging. Think of, if you have, you have understood what is forward chaining, what is backward chaining. Think how explanation facility can be incorporated in a rule based system. By explanation facility, I just want you to find out that if at any particular point a rule has stated a conclusion, okay, you have got fever, you have got malaria, for example, then if the user says why, that the system explanation facility should be able to tell the rule, present that rule which really concluded malaria, and might be that had some antecedents which have been found true, then which of, how did these antecedents were evaluated to true, how is it that these antecedents were found to be true, that should also be found out, which rules made these antecedents true. Okay. It is a little tough, but I am giving you a hint that what is the data structure you think will be helpful. Stack, the data structure stack that you know of will be immensely helpful, you can think about that. And in the next lecture, we will be mostly discussing about uncertainty management techniques, and first before that we will talk about certainty factors, and then we will proceed to other uncertainty management techniques. Thank you.